Okay. I was going to go over some stat stuff with you guys just to make sure that we're good with it. We understand it. These are some of the tricky parts as I was going through making up y'all's test for this unit. These are some of the things I wanted to make sure that y'all really understand. I'm laughing because in the background, my son is doing his science homework and we're trying to figure out what state of matter lightning is. And so we're having an argument about lightning and states of matter. So, anyway, fun at home learning. All right. So, I wanted to make sure that you'll understand what correlations are. And when you look at correlation, it's the measure of the extent to which two variables change together. So if you look at two different variables, how are they related? How are they changing when you put them on a graph? And so for correlations, I'm going to move my mouse. You're always going to use a scatter plot. And basically, when you put all the different points on a graph, then whichever way the dots tend to move or what it looks like they're moving, what direction is, that's the relationship between the variables. So we're going to use correlations to tell how well either factor is going to predict the other. So when we're looking at, when we're looking at our scatter plot, now obviously this is ideal and you're really not ever going to get a scatter plot that like is this nicely defined. But if it is sloping up, if the dots tend to go up and to the right, it is a positive correlation. And when we talk about positive correlations, that's our correlation coefficient. So it's the measure of the relationship. So it's going to range anywhere between a -1 to a +1. And the closer it is to 1, whether it's negative or positive, that's the stronger the relationship. So if you have a correlation coefficient of 0.08, it is not a strong correlation. So you don't have a very good relationship between the two things, between your two variables. Correlation coefficient, you're also going to see denoted as an R. And so it's just range. That's what the R stands for. So if it's positive, your dots are going to go up and to the right. If it's negative, they're going to slope down. If there is no correlation, so if we're stuck at 0, they're just going to kind of be all randomly over the place. So you just need to kind of look at which way your dots are going. So like this one, if you are looking at the correlation between height and your temperament, okay, this was one of the ones in your book. If you look at the dots, you can kind of see that they tend to go upward. Like the higher you get, the higher your temperament goes up. So because it slopes upward, that's a positive correlation. All right, so I wanted to give y'all 2 examples just to kind of help you make sure that we get what's going on. All right. So if we're looking at the number of pages in a book, and that's correlating with the number of times it's checked out from the library. So if we have 30, I'm just randomly making up a graph over here. All right. All right, so the number of times a book is checked out from the library versus the number of pages it has. More than likely, if it is a smaller book, it's going to get checked out more frequently. So then like you could say, oh, this is a really short book. Okay, but then as the number of pages start to go up, you're probably going to have that book checked out fewer times because it's so long and either people don't want to read the book or it takes a long time. So because the line tends to go down this way, that would be a negative correlation. Just to give y'all that example. And then the number of movies a person attends correlates with the amount of popcorn consumed. So if we would do this again, so if we have our movies, amount of popcorn, if you just go to one movie a month, you're probably like only going to buy like one thing of popcorn. But the more movies you go to, just because you're going to see more movies, the amount of popcorn is going to go up. So since the dots tend to track that way, it's a positive correlation. Okay, so just kind of keep that in mind. But really, you just need to know that close to a 1 or a -1 is a super, super strong correlation. So keep that in mind. 1 is your number to know. Okay. If we're looking at statistical significance, this is how likely is it that the result of your experiment, whatever data you get, what is the likelihood that your result occurred by chance? And you have to have proof beyond a reasonable doubt that the scores that you get are valid and chance had no part to play in the results at all. Okay, so the best way to remember statistical significance is the likelihood that a result could not have happened to chance. If it's less than 5%, then your findings are statistically significant. So I wanted to make sure you get that number and understand what statistical significance is. Okay, when we are looking at skewed distributions, this came up the other day in class, like how do you know which way something is skewed? So here's what you need to remember about skewed distributions. The tail tells the tail. So you need to look at the tail of your graph, which part is the longest part of the graph. So whichever way it tracks off, that's going to tell you if it's positively or negatively skewed. So if it goes this direction, it's negatively skewed because we're going like backwards on a number line. But if your graph trails off this way, it's positively skewed. All right. If we are looking at a normal distribution, not a positively skewed or negatively skewed distribution. Normal distribution is your bell curve. And my bell curve actually looks halfway decent today. And so normal distributions are going to be used to look at average scores or like where your scores fall in relationship to your average. So if you have your mean, that would be like there in the middle. You need to pay attention to standard deviation. So one standard deviation from your average, okay, is 34% on either side of the mean, which would be a total of 68%. Usually they should only ask you these numbers, but if not, you need to know that this is the total number for one standard deviation. So like if you're, I'll use my Post-it notes. Okay, so here's your average. This area in between, that's one standard deviation. So that's 68%, but realize that 34% falls on the right of your average and the other 34% falls on the left of your average. If you're looking at two standard deviations, okay, that's 95% of all of your scores in total. So you would have that. So 47.5% goes on one side, 47.5 goes on the other. But like I said, so long as you can remember 68 and 95 as the total amount of space from your average, you should be good with normal distribution. And then I wanted to go over independent and dependent variables again real quick. Oh, I left my examples in the other room. That's fine. All right, so your independent variable is what is changed. So what you are purposely going to change in your experiment to prove a result. So if you're writing out a statement, what is changed, that's the if. So if blah, 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 then blah, blah, blah. So like if leaf color is dependent on temperature change or variations in temperature, then I left it. I'm going to try to go find it while I'm talking about independent and dependent variables. And then, I can't see myself in the background. It's fine. All right. So your dependent measurement is, or dependent variable is what is measured. So we're talking about leaves and color change and temperature. What is measured and then what is changed? Hold on. I'm going to pause this and I'm going to go get my example. Okay, I got my example. All right, so here is an example of an experiment so we can look at independent and dependent variable. If leaf color change is related to temperature, then exposing plants to low temperatures will result in changes in leaf color. All right. So the independent variable. Hold on. The struggle. All right. Oh, okay. So if, and then, so the way I look at independent and dependent variable is I always do it backward. What am I testing for? And then what am I going to change in order to get that? So I'm looking for leaf color. Okay. So leaf color is the dependent variable, right? Because I'm looking to see what color leaf I get. And then what am I changing? I'm going to change the temperature that the leaf is exposed to in order to get that color. Confounding variables are any kind of outside factor that could mess with your experiment results. I call those the what if, because if you have a kid, well, what if you do this? Or what if this happens? Or what if that happens? So those are just confounding variables. And then don't forget when we do experiments, you have different groups. You have your experimental group, which is the group that's going to receive whatever treatment, or they're the ones that are exposed to the independent variable. Then your control group, these are the ones not exposed to the independent variable. So this is kind of like your baseline. It's your control, which is why it's called the control group. And they're used for comparisons. And then you also have random assignment. And that's where you're going to randomly put people into the experimental or the control group. That way you get better results. If you really, really want good results, you do a double blind where you don't know as the researcher who's part of the experimental group and who's part of the control group. You don't know either one of them. And that way, when you go and you look at the results or you conduct the experiment, you're not unconsciously biased one way or another. So hopefully that clears up some stuff with statistics. Like I said, there are going to be examples of independent and dependent variable on the test. There will be stuff about scatter plots, coefficient, standard deviation, stuff like that. So I will have a review for y'all before you take the test again, but hopefully this just clears up some stuff for you guys.